All right, well, everybody's filing in. Let's get this session started. Thanks everybody for coming to session 5A on tools and modeling. One of the backbones of our community that basically all of us rely on. I'm Matt Sinclair. I'm an assistant professor at the University of Wisconsin, and I'll be chairing this session. And we have four interesting and diverse talks from all over the globe to hear about. Without further ado, first I'm going to introduce Joseph Rogers, who is speaking about AIO today. And Joseph is a fifth-year PhD student at NTNU in Norway, and his research focuses on performance profiling and performance modeling to enable early-stage design analysis. Joseph, take it away.
So thank you very much for that introduction, and thank you to everyone that's here to hear this talk. So it's my pleasure to present AIO. So before I can really get to the meat of my talk, I first need to introduce you to somebody who's going to help me out with this story. And that somebody is Bob. So Bob is a software developer, and Bob's problem that he has to deal with today is how to effectively accelerate 3x3 image convolution. And this seems like it should be a pretty simple task, typically, but Bob is now living in a world of emerging heterogeneous architectures. And so things are not quite as simple as they might once have been. These days, if we look at this kind of von Neumann-y diagram, traditional way to distribute transistors is where we have all of the compute on one side, and it does compute-oriented things with maybe a little bit of SRAM, and then all of the DRAM or memory-type transistors are on the other side of some interface, and they're only used for memory. And so we call these DSAs for all types of devices like this in our work. But of course, we have these emerging flavors of processing in memory now. So we have a thing called SCM, which is SRAM computation memory, where now a huge proportion of your compute-oriented transistors are being used for some sort of massive SRAM array that has compute capabilities. We also have flavors of analog DRAM processing in memory. So the Ambit platform is a good example of this. And there's also near data processing, or processing in near memory, depending on the acronym you choose. This is a thing like the UPMEM architecture, where they have taken DRAM transistors, but then what they've done is they're implementing in-order scalar CPUs, just using that process. So this is all very interesting for Bob, because Bob is getting nervous now, and he's thinking to himself, oh dear, there's all of these emerging devices available. Where should I port my code? Where should I spend my effort on? So this is where we come to the idea of early-stage performance analysis. So what can Bob use to do this? Well, the roofline, of course. So if Bob takes the roofline and he wants to apply it to a classic device like a DSA, it's absolutely possible for the roofline to be very excellent at this, and it can capture performance trends very, very well. However, if you try to apply roofline to some of these emerging devices, you often have a problem coming up where the performance trend is not possible to capture with roofline. And in this case, for UPMEM, it's very easy to run into problems with limited algorithmic parallelism. And it's just simply the case that roofline doesn't have possibility to show those kind of trends. So it's too high level. It doesn't account for the key performance phenomenon that lead to this. So this is sad for Bob. But are there other things that Bob could be using instead of roofline? Something lower level? And the answer is yes. For all of these types of platforms, there's a variety of options that exist, and they all have a similar problem, however, and that's that all of them are domain-specific in one way or another. So you would have to use a separate one of these for every type of hardware domain, and they contain specific details that make them accurate but not generalizable. So this makes Bob very sad. Now what is Bob supposed to do? So there's a missing piece here, basically. We want to have an abstraction that fills this gap between the high-level, easy-to-use roofline and the low-level, accurate but difficult-to-use domain-specific models. And so this is where our work comes in, which is AIO for architecture-independent operations. The idea of an AIO is that for any given program, you can define a piece of work in it that's data parallel in some way, and then conceptually the same across all of the devices that you're considering. So let's go back to Bob's problem of the 3x3 image convolution. Conceptually, you can think of all of the instructions needed to do one convolution, one pass through the image filter, as the operation. Go in at this abstraction level instead. And so this would be defining the AIO as everything inside of these two inner loops. And then what happens is, once you've defined it at this level, you map the AIO to the device-specific instructions, where if we're considering acceleration on the DSA versus the UPMEM, the DSA is able to do the AIO using dedicated MAC instructions, and the UPMEM, because it's a more compute-limited device, it doesn't have the same capabilities of the DSA, it only has multiply and addition instructions, perhaps. But fundamentally, they're both able to do the same AIO operation, they just go about it in a different way. So this enables a common abstraction to compare the performance of these two devices by looking at their respective AIO throughputs. So how can we apply this in a real example? Well, one thing that we did is we created a simple performance model leveraging the AIO concept to try to apply this in the real world. And this is called ACME. And this is just one way to apply the AIO concept. There are certainly others. So if we start again with the concept of this image convolution, we then have our kernel code that we want to accelerate and a set of devices that we're interested in testing it out on. From those two things, we extract a set of kernel parameters and accelerator parameters that are just high-level descriptions of these devices, and we pipe them into the ACME model, which is just a really simple set of algebraic equations. And from that, we get cycle estimates of the compute time, the time spent waiting for non-masked memory cycles, and the time spent invoking the device. So for all of the details on exactly why we think these are good parameters to choose and how to go about getting them, please read the paper or talk to me in the poster session. And we demonstrate that using the AIO abstraction along with ACME is actually pretty accurate in a lot of cases. So we look at it on 4 devices across 173 configurations, and it's pretty decent. So this is ACME. It's a very simple performance model, but you can apply it to many diverse types of accelerators simultaneously. So Bob is back now, and let's see how Bob would use ACME and AIO together for Cholesky decomposition. And now Bob is going to consider all 4 devices and see which one is going to be the best. So his goal is to find the fastest device, but he has a variety of different input matrix set sizes that he has to consider. One of the problems that Bob is working with, though, is that he has extremely high uncertainty for the AIO latency on each of these devices. Well, that's okay, because we can just parameterize that when it's with ACME. So if we graph out the performance with this uncertainty on each of the devices, even with a huge plus or minus 10x in either direction, you can still get a lot of actionable information pretty quickly. So it's very easy to see that across all matrix sizes, Ambit is the slowest in all cases. So Bob really knows very little at this point, but he's already able to say that we shouldn't use Ambit for this particular problem. And once again, that's due to limited algorithmic parallelism. So it's not because Ambit is fundamentally a bad accelerator, it's just ill-suited for this particular kernel. So takeaway from this is that very simple models, you can get very good actionable information even when you don't necessarily know very much. So if Bob wants to continue for the 3 remaining devices, he's going to have to do some work then. And let's say that he does this, and he reduces his uncertainty for the AIO latency down from 10x to 1.25x. At this case, if he goes in and just looks at the DSA and SCM, now you can see that the SCM is the slowest in all cases. So if we look at detailed reasons for that, that's because this is control core overhead that makes it slower than the DSA. And finally, just looking at the DSA and the UPMEM, actually the best performer depends on the input set size of the matrix. So for the smallest matrices, they've got very similar performance, In the middle, OpMem is faster, but then at the largest sizes, the scratch pad in the OpMem overflows, and so it then becomes worse than the DSA. And this is kind of an interesting observation, I think, that the input set changes the performance so much, and we actually were able to get access to the real OpMem hardware, and so we validated these performance curves. So now Bob is happy because Bob knows a lot about which device is preferable, and depending on the relative distribution of matrix sizes, he can make a choice. So to conclude, models like Roofline are quick, but they're too high level for use with diverse accelerators, whereas the domain-specific models are very accurate, but they don't generalize to multiple devices. And to fill this gap, we propose AIO, which is an abstraction for comparing diverse accelerators. And to show AIO's utility, we propose ACME, which is a simple performance model. And we demonstrate that AIO and ACME can be accurate, and that even when the accuracy of it is limited, it can still be quite useful. So thank you very much. We have some interactive examples online if you want to try ACME for yourself. And if this is interesting to you, please come and talk to me at the poster session.
Great job. As always, please come up to the microphones if you have a question, announce your name and affiliation, and go ahead. Yes.
Hi, I'm Angshu Parashar from NVIDIA. Great talk and really fascinating piece of work. Thank you for sharing with us. So the examples of the accelerators that you fit into this abstraction were relatively simple. At what point does the abstraction start breaking down?
So I think that what we noticed in our testing is that the AIO abstraction itself is one thing, and then the performance model we create, ACME, is a separate thing. And ACME is really what breaks down first. So for instance, on the OpMem, you have a lot of independent threads working independently and having to share data and maybe communicate. And we don't have any parameters for this thread communication overhead, for example. So this is an example of something that, if that's a major scaling issue, then we are not going to capture that sort of performance scaling. But I would say that the solution in that case then is to use the AIO concept, but create a more appropriate performance model than ACME.
Thank you.
Maybe Shai Galon, Google, maybe along the same lines, not just the accelerator, but the program that you're actually trying to model might be difficult. And how do we take this concept and apply it to a database?
So how do we take the AIO concept and apply it to a difficult program? Oh, yeah, I think definitely the examples that I showed, like image convolution, it's pretty simple and digestible. But if you want to do something more advanced, like an LLM, because that's very hot, for example, right now, then the correct thing to do in that case, I think, is you want to go in at an abstraction level where the key thing that's most important is to choose the AIO at an abstraction level that makes sense. So maybe this is going to be one inference or something like this at the level of a whole LLM. And that will be make some work on your part, because then you have to figure out all of the back-end instructions that a device would have to use to do an AIO at that level of abstraction. But I think fundamentally, there's nothing stopping it from being applicable there.
Okay, I'll catch you later.
So I know the timer says we're about to be done, but since you finished 1 minute early in your speech, why don't we go ahead with one last question?
Chunyu from ByteDance. My question is, can you use ACME to explore hardware design spaces, like accelerators?
ACME to explore what design spaces?
Hardware, the accelerator.
Oh, yeah. So this was kind of an interesting thing we thought about a little bit, and we looked at other models like Aladdin that are doing this for the HLS space, for example. And I would say that the best way to use ACME if you're a hardware designer is to try to do it as early in the design stage as possible when you're going to have the maximum, the earliest decisions have the maximum impact on your design, I would say. But yes, I would say that if you can try, like we have a good example actually in the paper where we parameterize adding different numbers of cores to a DSA and see how that scales the performance on different programs and when you run into like memory bandwidth bottlenecks and stuff like this. So yes, we look into that a bit.
Thank you.
All right, let's thank our speaker one more time.
Thank you.
While we're getting set up for the next speaker, why don't I go ahead and introduce him? So our second speaker is Jun Hu, who is a second-year PhD student at UC Berkeley, advised by Kjolstad Asanovic, and he's interested in SoC design and RTL simulation methodologies, and is currently working on the FireSim project. And he is going to tell us how he's going to take an axe to FireSim with FireAxe.
Testing. Okay. Hello, I'll be presenting about FireAxe, which is an open source platform for partitioned FPGA-accelerated simulation of large-scale RTL designs. So the talk overview is like this. I'll provide some background and motivation on why we started talking about building this tool. And then I'll explain about FireRipper, which is a compiler that enables partition simulations inside FireSim. And then I'll move on to explaining about FireAxe's flexible FPGA platform support that enables us to democratize fast, large-scale RTL simulations. And then I'll provide some usage examples to explain how easy it is to use FireAxe, and then I'll conclude the talk. So to provide some context here, there are some differences between FPGA simulators and prototypes. So let's say you have a target design that you want to simulate. The RTL here is running at 1 gigahertz, and you attach a DRAM with 100 nanoseconds of latency. Here, the SoC will see 100 cycles of DRAM latency, but if you just plop the RTL on an FPGA that's running at 100 megahertz, now the SoC sees only 10 cycles of DRAM latency, so all the performance measurements that you're performing is wrong. So FireSim deals with this issue by adding queues to the I/O ports of the RTL and having models of the DRAM, for example, to provide the SoC with realistic DRAM latency. However, the problem of FireSim is that large designs don't fit in one FPGA. So let's say we want to simulate an SoC that contains 24 Berkeley out-of-order machines. They're 3-byte out-of-order cores with 0.8 millimeter square of ASIC area in a commercial 16 nanometer process. And you also want to simulate your memory hierarchy, peripherals, and I/O devices. And then the SoC area becomes into this gigantic 18.7 millimeter square of ASIC. And the problem is that the SoC doesn't fit in one FPGA, so we cannot simulate this design. So the solution is to, of course, partition the design onto multiple FPGAs so that we have higher simulation capacity. However, we don't want the designer to be hand partitioning the design because it's very error prone and it's very time consuming as well. So what we want to do is have a compiler that can automate this process away. So FireAxe's compiler ingests the input designer RTL as well as some compiler flags, and according to how the designer wants to partition the SoC, it'll perform some module grouping, and then it'll perform boundary analysis on the partition boundaries, and it'll do optional partitioning optimizations, and then it'll generate the communication collaterals. And the output of this compiler is fed to Golden Gate, which is a FPGA mapping compiler. And at this point, we have partitioned FPGA-accelerated RTL simulations. So I'll now move on to the details of FireAxe's compiler, especially on the boundary analysis and communication collateral generation part. So problems start appearing when you're trying to model combinational logic across FPGAs. So this is a design with 2 registers with some combinational logic attached to it, feeding it back to the registers. And when we partition the design onto 2 FPGAs, we wrap it in LIBDNs. This is basically attaching queues to the I/O ports. The value of B is unknown at this point because it has some combinational dependencies with the input port A, so we cannot send this upper token to the other side, right? Similarly, the value of D is unknown at this point because of some combinational logic. and you cannot send the bottom token to the other side. So the TLDR here is that there's some circular dependencies between two FPGAs, and the simulator will deadlock. To solve this issue, the compiler splits the channels in such a way that tokens that depend only on sequential logic can be sent independently to the other FPGA. And after that, tokens that have combinational dependencies between the input and output ports can be computed using the tokens from the previous step. So using this compiler, we partition a large out-of-order core. So it's a larger variant of Boom that does not fit in a single FPGA. It's 6 wide and has 216 ROB entries and 1.56 millimeter square in commercial 16 nanometer technology. And there's over 7,000 bits going through the partition boundary. And you partition the design onto 2 FPGAs running at 10 megahertz. We can boot Linux on this core that's partitioned, and we can run realistic benchmarks such as MBench. So thanks to FireAxe, we can obtain not only CPI stacks, but other microarchitectural performance counters so that we can perform DSC on these large out-of-order cores. Now I'll move on to explaining about the partitioning optimizations that the compiler can do. So the idea here is to use microarchitectural semantics to improve partition simulation performance and quality of the partitions. So if you zoom into the SoC, we can see that there's a lot of latency-insensitive boundaries, and this is because with just latency-sensitive boundaries, you cannot scale the design over a certain point. So the first type of latency-insensitive boundaries are ready-valid interfaces or decoupled interfaces, and examples of these in your design is your core bus boundaries, for example. So for these boundaries, what we can do is we can inject latency in between the interfaces to remove the intra-cycle synchronization required to simulate one target cycle. So this results in nearly a 2x increase in simulation throughput. However, injecting latency in decoupled interfaces introduces functional bugs. So to restore this functionality, we have to modify the target boundaries. And this, of course, introduces slight accuracy degradations. However, for early stage performance estimations, this is fine, and you can always fall back to the default compiler mode to obtain cycle exact simulation results later in the design cycle. There's other latency-insensitive boundaries, such as credit-based interfaces in the SoC as well, and examples of this is not-router-node boundaries. This is a very good boundary to partition across because there's no target boundary modifications required, because first it's latency insensitive, as well as there is no combinational dependencies between the input and output ports. Also, it's a narrow partition boundary, so it enables us to scale the design that we are simulating across this partition boundary very easily. And you can also map the SoC topology onto the FPGA topology, which also has nice performance characteristics. Now, I'll move on to explaining how the partitioning compiler has a synergistic effect with the FPGA mapping compiler. So once again, if you look at the SoC, there's a lot of modules that are stamped out multiple times, such as cores. And FireSim can employ a simulator-level multi-threading to save FPGA resources. So let's look at an example partition simulation. So here, the FPGA resource consumption is really proportional to the size of the target design that you're simulating. So here, it's proportional to the number of cores, right? So in FireSim, you have an optimization that enables us to save FPGA resources, or given the same FPGA resources, simulate larger designs. So what's happening here is that we're sharing combinational logic between the duplicate modules and replicating the sequential logic, and we insert hardware schedulers that choose the correct sequential logic to update for a particular host cycle. So this introduces to the designer a time versus FPGA resource trade-off, because you can now simulate larger designs, but you have to pay multiple host FPGA cycles to advance one target cycle. So if you're to do this in a monolithic FireSim simulation, now you're spending 4 host FPGA cycles to simulate one target cycle, so the simulation throughput is tanked by 4x. However, in a partitioned FPGA simulation case, we have an extra overhead of 10 to 50 inter-FPGA communication cycles. So this enables us to amortize the overhead of multi-threading hidden due to inter-FPGA communication overheads, and it provides the designer with a very nice trade-off space. I'll move on to explaining about the supported FPGA platforms in FireAxe. So we can run on Cloud EC2 F1 instances, so you can just launch a cloud FPGA instance, start working on FireAxe right now. And here we use direct peer-to-peer PCI FPGA communications to reduce the inter-FPGA communication latency. We also support local FPGAs as well, so we can connect Xilinx U250s with QSFP direct attached cables, and approximately we get a 2x simulation performance increase compared to the cloud case because we're using direct links here. There's some performance characteristics that we measured on a particular design that we're partitioning across 2 FPGAs. The y-axis over here is the simulation frequency or throughput. The x-axis is the partition interface width in bits. So we vary this bits by changing the number of cores that we're pulling out from the SoC. So we can see that we achieve a maximum of 1.8 megahertz of simulation performance and a minimum of 0.3 megahertz. And we can also see that as we increase the partition bits going off the FPGA, the simulation throughput decreases, and this is because of the overhead of serializing the bits going off the FPGA starts becoming the bottleneck. And we can also see by performing compiler optimizations, we get a 2x increase in simulation throughput. There's much more performance characterizations in the paper, so please look at the paper if you're interested. We also performed a lot of case studies. So first, we found that RTL bugged 3 billion cycles into simulation. And in FireAxe, this took only like a matter of hours. But to just reach this bug in software RTL simulation, it'll take weeks to reach. So it's really unreasonable to debug these type of systems using software RTL sim. We can also reproduce full-stack system-level effects that require simulating many cores or large cores as well. So I'll now move on to explaining how easy it is to use FireAxe. So let's say you want to partition this design onto FPGAs. So all you have to do is specify the mapping or the partitioning mapping of how modules will be mapped to certain FPGAs. You provide some compiler flags, and you specify the inter-FPGA communication link. And with this, you can start launching bitstream builds for partitioned FPGA simulations. And once you get the bitstreams, you basically have to specify mappings between the bitstreams and the FPGA slot IDs, and specify the inter-FPGA communication topology, and at this point, you can start running FireAxe simulations. So with less than 30 lines of code, we are able to build bitstreams and launch partitioned FPGA sims. So in conclusion, FireAxe enables agile teams to rapidly and accurately model large-scale designs with minimal designer effort. And it's dog-fooded, so it's actively used in multiple ongoing projects in UC Berkeley. And the compiler readily automates the partitioning process. So it ensures functional correctness of the partition design, it provides partitioning flexibility to the end user, and it also exposes performance optimization knobs. And it really requires minimal code to use this. And it's flexible and accessible, so you can run this on cloud and local FPGAs as well. And FireAxe is currently upstreamed in FireSim, so you can just git clone FireSim and start using FireAxe right now. And there's also documentation available. Thank you for listening, and I'll be happy to take any questions.
I see the questioners have already lined up, so go ahead, Luca.
Thank you, Luca Carloni, Columbia University. Thank you very much, very interesting talk. I have a question, maybe a follow-up, depending on the question. So when you were talking about the fact that the throughput in communication slowed down by a factor of 2, and then you talk about this is a small loss of accuracy, if I understood it correctly, but we are early in the design process, and this is fine. What do you mean for loss of accuracy? Functional accuracy, or?
No, the functional accuracy is maintained. It's just that we're modifying the target boundaries a bit so that we can retain the functionality but remove this synchronization over it. So because we're modifying the RTL that we want to simulate, that introduces errors compared to the original RTL that we wanted to simulate.
But errors, so RTL as a state, there is this notion of state, which is basically the content of the flip-flop at each cycle. When you say that you may introduce errors, you are talking about errors in the logical state, or you're talking about errors in the relative performance of the different components?
So it's relative cycle count, the number of cycles.
I see.
Yeah.
But you know you know exactly where you introduce the latest.
Yeah, exactly.
So you could
Oh, yeah, I see what you're saying.
You could subtract that error.
Yeah,
because you know statically where it is.
So, of course, you can statically do some analysis, but these types of errors really depend on like the dynamic state of your SoC as well, right? So depending on the workload, the error can change. However, you can try to build like statistical models that will try to like take off these errors after running the simulation as well.
And we can follow up on I think that if you maintain the RTL equivalence in a latency-sensitive manner, you may be able to handle that. But we can take it offline.
Yeah, cool.
All right, let's move on to the second question then.
Hi, Jose Cano, University of Glasgow. So I was a bit confused about the talk. Initially, you said that you were limited by the size of the memory of the FPGA. Is that correct?
We're not really limited by the backing DRAM on the FPGAs.
Right.
We're rather limited by the number of LUTs.
Right, by the fabric itself, right?
Sorry?
By the fabric itself, FPGA fabric.
Yeah.
Yeah, so because initially I thought that was the workload was limiting you to map on one FPGA, then it seems that is the size of the SoC. The size of the SoC, you can always scale it down, right? So you can always have something smaller, right? Simulate, and then scale it up, right? Yeah. So second quick question, you said that you were running realistic workloads. You didn't show us any realistic, what are the workloads you are running?
So here in the paper, we run a Golang application, and we reproduce tail latency effect induced by garbage collection. Mm-hmm. And we needed FireAxe because we had to simulate many cores to induce this effect.
Okay. Okay, thanks.
Yep. All right, let's thank the speaker one last time. So our third speaker in this session is Nikolaos. Nikolaos is a second-year PhD student in the Computer Architecture Lab at the University of Athens with Dimitrios Gizopoulos, and his research interests include reliability, silent data corruptions, and CPU simulation and modeling. And he's going to tell us if your CPU has been lying to you and violating the Hippocratic Oath with Harpocrates.
Okay, let's go back. Okay, great. Good evening, everyone. My name is Nikos Karystinos, and I'm going to be presenting our paper named Harpocrates, Breaking the Silence of CPU Faults Through Hardware-in-the-Loop Program Generation. So just a bit of quick background on the term silent data corruption. So data corruptions in the CPU stem from either external factors or internal factors, where the CPU itself has some kind of defect. And the interesting thing is that when data is corrupted, we have three possible outcomes. One, the corrupted data is discarded by the computation, so it doesn't influence the final result, which is good, no corruption. Then the second case is that some kind of assertion is triggered, either from the hardware or the software, or we get a crash, which I will say is again good, because this is a loud corruption, and we have an indication that something clearly went wrong. The bad stuff happens when the computation's result is influenced or the corrupted data is persisted without us having any indication that this happened. And this is what we call a silent data corruption. So, it turns out, okay, how often would you expect this to happen? It turns out it happens a lot more than we thought, and this is especially apparent at scale. So to be more specific, we have three major hyperscalers reporting on multiple data corruption events tied to faulty chips. First up, Meta, with the paper Silent Data Corruptions at Scale. Then Alibaba, with the paper Understanding Silent Data Corruptions in a Large Production CPU Population. And then Google, with the best paper name award, I would say, with the paper Cores That Don't Count. So it's clear that there's a problem here. So let's put this into numbers. How many cores are reported to be defective? On the left, you can see the statements from the corresponding papers. And on the right, you can see a DPPM magnitude summary taken from figure 1 in the paper. And notice that we're talking about almost 1,000 dppm, which is 1 in 1,000 cores is faulty. And keep in mind that in some safety critical domains, less than 10 dppm is required. Let's go ahead and briefly visualize this magnitude. So this is a 10 by 10 grid, 100 CPUs. 32 by 32 grid, about 1,000 CPUs. 100 by 100 grid, 10,000 CPUs. If we take the average of the reported dppms, we will get that we expect 6 to be defective, which is clearly a problem. Maybe the back row can't see it, but yeah, I can see the problem. OK, so this problem is a call to arms, both for hardware and software. And there are many mitigation techniques on each side. But usually these methods are kind of orthogonal, so they don't interact too much. And our approach tries to combine a software method, namely automated test program generation, with hardware information. So we're trying to get microarchitectural level information to incorporate into the automated program generation. So what's Harpocrates? It's essentially a tool chain paired with a methodology that generates, grades, and iteratively refines functional test programs. Our main idea lies in increasing what we call the hardware coverage of the generated programs. And intuitively, you can think of high coverage as the fact that the program diversely excites a target hardware structure. And here, our core hypothesis is that when you increase the hardware coverage of programs, what you will get as a result is improved fault detection capabilities. So let's talk a bit more about coverage and detection. The question about coverage is, how do you quantify this? It's a bit abstract. So remember, it's just a fast proxy metric that we hope correlates well with detection capability. So we simply define coverage as any objective function which we construct to correlate well with detection capability. And it has two core desirable properties. First, quick evaluation, ideally one program execution. And secondly, incorporation of hardware-level information. So it's hardware aware. And just to give a quick example before we move on, just to give a quick example on coverage. Imagine you want to define coverage for an integer adder. The simplest way to do that would be just to count the number of activations in the adder, because that is fast to measure, just in one program execution. And also it's hardware aware, because you're actually looking into the microarchitecture, what the microarchitecture is doing. OK, so fault detection capability is the final test program, the premise, the final test program quality metric. And the premise in Harpocrates is that we optimize coverage to get some optimized programs which possess superior fault detection capability. In our setup, we measure the final detection capability with statistical fault injection in GEM5, where we can inject faults of different types in more than 50 components of the microarchitecture. So let's summarize Harpocrates' contributions. First, we implement a novel code generation and mutation engine for the x86 ISA. We have also built hardware-aware analysis and metrics on top of the GEM5 simulator, which essentially help us quantify hardware coverage. And of course, the main contribution is an end-to-end hardware-aware test refinement methodology, which is adaptable to any ISA, any hardware structure, and any fault type. So let's see Harpocrates in action. We start with the program generator, producing the initial program population. This population then is fed into our evaluator, which is built around the GEM5 simulator, to measure the hardware coverage for the target component. The programs are ranked based on that coverage, and we keep the top K fit test, which we pass on to our mutator. And then our mutator produces variants of these top K programs, and in tandem with the generator, a next program population is generated, which is again evaluated, and the iterative refinement cycle continues. And this part in Harpocrates is a single tool, which we call MusicGen, which stands for, mutator and sequence generator, very original, I know. Yeah, so let's look into MusicGen's architecture. So it's based on the open source IBM research code generator named Microprobe. Microprobe only supported the PowerPC and RISC-V ISAs, and we significantly extend the framework to incorporate the x86 ISA. Microprobe consists of two main modules. The architecture module, shown on the left, which retains all architectural information, and the beautifully decoupled code generation module on the right, through which you can specify compiler-like passes to drive the code generation process. And this decoupling is crucial because these passes are highly reusable even across ISAs. We have also built another layer of tooling to orchestrate generation and mutation called the manager, and of course, our program mutation engine. So let's see if this actually works, though, right? We evaluated the pipeline of Harpocrates on 6 key hardware structures and 2 distinct fault models. We choose overwritable single-bit upsets for the bit array components, the integer register file and the L1 data cache, and for the 4 functional units, we choose permanent stack at gate level faults. So let's see the evaluation graphs. We don't have time for all the components, so I'll just show 2 and then a summary graph. So first up, the integer register file. And I want you to keep in mind a few points here. Firstly, the top left graph in this slide is for Harpocrates, and it shows the sampled coverage right now with the dots. The detection is going to come in soon for all the graphs with the cross symbol. But this graph for Harpocrates shows the sampled coverage and detection across the Harpocrates optimization. Notice that this isn't the case for any of the other frameworks we compare against. We just give the coverage and detection numbers of their programs. There is no progression on the bottom graphs. There is no optimization happening. The top graph, optimization is happening. OK, so as you see, the coverage is going up. And for the other frameworks, the coverage is like seems pretty random around some baseline. We compare against MI bench, 12 workloads for MI bench, which are general purpose workloads, just for a baseline. Then we also compare against about 300 programs from Silifas, which is an automated test generation methodology as well. And then about 21 tests from OpenDCDAG, which is an open source CPU testing framework from Intel. And this is the detection. As you can see, Harpocrates outperforms the rest of the frameworks by 10x in the final detection achieved. And also, I want you to notice that we have actually proved the whole premise. The premise was, if we increase the coverage, we will get better detection. And notice that this is exactly what's happening. We have a linear correlation. If you look at the bottom graphs, there is no clear correlation between coverage and detection. So this is another example, the integer multiplier. And notice again that Harpocrates manages to achieve almost 100% detection for the multiplier, whereas the average program from the other frameworks achieves a mere 60%. And remember that for functional unit components, we inject with permanent faults. So achieving 60% detection for permanent faults is really unsatisfactory. Many go undetected. And we managed to do this in just 1,000 Harpocrates refinement cycles. And this is the summary graph for all 6 components. And as you can see, Harpocrates is dominating across the board. The integer adder is an easy component to test for. So all of the frameworks have pretty high scoring programs there. But the 2 multipliers, Harpocrates manages to do much better than the competition, and for the cache as well. And the register file is a clear 10x win. So yeah, that's all. Thank you. Any questions?
Shai Galon, Google. You're comparing for the faults you injected. Have you tried looking at, you mentioned Silifas, any of the faults that were actually found in CPUs by Silifas and seeing if this actually finds them?
Yeah, so that's our exact next step. We're planning to evaluate on real systems and trying to catch real faults. because this is just proving on the simulation infrastructure, proving that the idea is working. So we're working towards real systems and catching real bugs.
Okay, thanks.
Ben Feinberg, Sandia National Labs. Great talk. So I'm trying to understand, how do you make sure that the hardware structures in your simulator are can match real hardware, so I can, to correlate how these for a fault in your simulator actually correspond to a fault in real hardware?
Yeah, so that's another good question. Yeah, we can't know for sure, because no one knows what your adder looks like in your Intel, AMD, whatever chip. So modeling always has some trade-off there. But I guess this is kind of the best we can do. We can optimize our programs with a good enough model, and we're hoping to catch bugs on real hardware. But I don't know. Do you have any models of actual others to give us? I'm guessing
No, I
not.
have the same problem. That's why I asked.
Hi, very nice talk. Freddy Gabay, Zabro University. I wanted to ask about the generator. Can you elaborate about this? I mean, is it like a random, or is it aware about, does the generator...
Yeah, the generator is a random...
Design
Sorry,
itself?
go ahead.
No. I mean, is it aware of the design details or the design netlist? How the generators operate in your scheme? I mean, you showed the generator there.
Yeah. So the generator is responsible for generating the programs. What we do is we've built on top of microprobe essentially, and the generator is.
Is it random? I meant, is it
Sorry?
random? Is it random? It generates things randomly,
Yeah,
it's
a random, but it can be constrained as well. So we can guide the generator to use a specific set of instructions. But for these experiments, we let it do a random selection of instructions mostly, and we let the coverage we define guide the programs towards. So you do a lot of mutation, a lot of random program generation, and then coverage guides the optimization towards where you want it to go. So that's the main idea. But yes, the generator is random in nature. But you can do structured generation as well. The framework is really flexible.
It's really wonderful to see there's so many questions, but we are over time on this talk, so I'm going to suggest at the poster session right after that you talk to him then. I do apologize, but excellent work. Let's thank the speaker one last time. While Nathan is getting up here and getting set up, I will point out if any of you are interested in just making a higher accuracy, higher fidelity Gem 5 CPU model, don't let it just be Nikos's problem. I'm definitely happy to chat with you and see how we can make that happen. In the meantime, let me introduce our last speaker. Our last speaker is Nathan Zhang, who is a final year PhD student in Kuhnle-Yakutin's group at Stanford, and his interests broadly lie in making Dataflow systems more accessible, ranging all the way from programming abstractions to compilers and simulators. And he's going to talk to us about his work on Dataflow abstraction machine simulation, which hopefully will not be too abstract.
Thank you, everyone. So hello, I'm Nathan. I'm a PhD student in Kunle's group, and today I'll be presenting the Dataflow Abstract Machine Simulator Framework, or DAM for short. So simulation sits at the heart of modern architecture research, underpinning almost every architectural contribution over the last few decades. And hardware-software co-design plays an increasingly larger role in our designs today, and these new systems frequently require bespoke simulators. In particular, Dataflow now dominates much of the modern accelerator design space, including large-scale machine learning systems. Simulation helps with the exploration and development of both the applications and the architecture, and some of our collaborators are also looking at ways of taking our simulation all the way down to RTL. However, high-performance simulation is hard, but doubly important as our workloads keep increasing in size. To make this work, we need abstractions which are amenable to parallelization. We need a system which can automatically schedule and load balance across workers, and we need one that synchronizes as necessary to ensure correctness. Now, it's worth noting that machine learning itself is naturally data flow, feeding batches of data through an operator graph. And to reflect that, many modern ML accelerators, particularly commercial ones, are also data flow. Data flow's scalability edge makes it a very attractive paradigm for building high-throughput, large-scale accelerators. So in rough order of compute capability, we have Plasticine, a chip that our group designed, which sat at 12.3 teraflops. Then there's Graphcore's GC200 IPU, which comes in about 250 teraflops. Sambanova's SN40L then more than doubles that at 638 teraflops. And finally, Cerebras Systems, which is somewhat infamous for their dinner plate-sized accelerators, recently announced their WSE3 at 125 petaflops. Even when the underlying accelerator isn't data flow, the overarching systems generally are. Here we have Pathways from Google, which is a data flow system built on top of TPUs. And on the right, we have the DGX H100, which again overlays a data flow model on top of GPUs. So I think it's pretty clear at this point that between the data flow applications, data flow accelerators, and data flow systems, that the future is data flow. There are three major challenges today in data flow simulation. The first major challenge is that there's no real consensus on what nodes are needed. Hardware design exploration changes rapidly. Designers often don't know what nodes are actually needed. Secondly, the frequent low latency communication between components in a data flow system means that synchronization in the simulation becomes incredibly problematic. An efficient scheme will need to be indifferent to both the simulated frequency and latency of communication. And finally, channel behaviors play a major role in both the correctness and efficiency of designs. Deadlock and pressure-induced stalls are common design bugs which plague data flow systems. DAM's proposition is quite simple. We'll provide a framework for building simulators which features a simple and productive interface. We'll automatically handle parallelization and synchronization to make sure that your simulation is fast and correct. And we will scale from a laptop or a local workstation up to the largest cloud instances available today. Now, there are a few things that I would like to highlight that make this possible. First, we have a new communicating sequential processes-based interface. Consider a node which merges inputs from two streams, taking the smaller element each time. In DAM, each component is modeled as an individual process. External connections are then modeled with optionally bounded channels. And each component will have its own local notion of time, so you can change it as needed. The second thing that I'd like to highlight is a pair of pairwise synchronization primitives which minimize overhead and are agnostic to the number of simulation workers. The first leverages release-acquire atomics, which many of you are probably familiar with. The second uses futexes, which are fast cooperative scheduling operations supported by the operating system kernel, like Linux. And these together are the key to scaling to thousands or tens of thousands of components across hundreds of workers. Now, if you're curious about understanding more details about these concepts, you can probably find me at the poster session, read the full paper, or just email me. But by combining these two, alongside multiple other techniques in our paper, DAM produces a new notion of time, which we call asynchronous distributed time. There are three classical notions of time in simulation. First, there is cycle-by-cycle simulation, which is used by most ad hoc research simulators, most famous, and there's also GEM5. However, this scheme is plagued by synchronization overhead, resulting in slow simulation speeds. The next improvement over that uses time quanta, which instead synchronizes once every few cycles. Unfortunately, this runs the risk of introducing errors in the form of race conditions between synchronization points. However, because it's so much faster, This is the approach used by simulators such as PAR-Gem5, Graphite, Sniper, and the Structural Simulation Toolkit. Finally, there are optimistic simulators in which there aren't really any errors, just happy little invalidations. But due to the complexity and engineering effort involved, this scheme is actually relatively rare to find in simulators. To the best of our knowledge, the only current academic simulator that uses this scheme is the Swarm Architecture Simulator from MIT, and we're not aware of any general purpose framework that uses this method. Our scheme instead relies on cooperative scheduling for correctness and work stealing for load balancing, thereby avoiding both global synchronization and invalidation. You know, to really summarize it, time is really like a big ball of time, wibbly-wobbly, timey-wimey stuff. You don't really have to worry about it. But to show the benefits of our techniques, we'll now dive into a few comparisons. Here, we have an artificial benchmark against the Structural Simulation Toolkit, which is the state-of-the-art simulation framework and uses the time quantum method. We ran this on a Google Cloud C3 high CPU 176 instance, which is an 88-core hyper-threaded Sapphire Rapids machine. It's an artificial benchmark consisting of a varying number of reduction trees of depths 8 or 10, and we computed Fibonacci at each point to pretend like we were doing work. We then imbalanced some of the workloads, so some of the nodes do 16 times more work than others. We found that DAM is at least 3.3 times faster than SST and up to 15 times faster on smaller problems. DAM also enjoys a larger advantage when handling imbalanced workloads, up to an order of magnitude faster, even when we have very large problems to amortize that away. After we built the simulation core, we started porting over our ongoing research projects. Our most pressing use case was simulating sparse tensor machine learning, where we wanted to figure out which modifications to the sparse abstract machine, or SAM, were necessary to support these large sparse ML models. There were two primary drawbacks with our old system. First, the simulator was too slow, taking hours to days for just single layers, and running entire models was completely out of the question. And secondly, the simulator was too verbose, which meant making modifications very error-prone and very difficult to debug. So to compare our two implementations, we picked 3 sparse tensor algebra kernels from the original SAM paper, sampled dense-dense matrix multiplication, sparse matrix multiplication, element-wise addition, as well as multi-headed attention, or MHA, the key kernel underpinning and bottlenecking transformer models. Depending on the workload structure, DAM achieves between a 33 times and 4.5 order of magnitude improvement in performance. And these performance improvements increase as the problem sizes get larger as well. But these comparisons are limited to what we could get out of SAM in 2 days. Thanks to its parallel runtime, DAM scales well with the amount of parallelism exposed by the workload. When simulating an unparallelized implementation of a batched multi-headed attention kernel, DAM took 622 seconds, or a bit over 10 minutes. As we parallelize that implementation by 64x, the simulation actually dropped down to 14 seconds, or about 40 times faster. And this also provides additional incentive to start thinking about parallelism earlier, instead of punting it to the end. DAM also scales well with the number of worker cores. Here, we again have the same C3 instance, and we looked at various different sizes of multi-headed attention. Inner IP and OP here refer to inner and outer parallelization factors of the multi-headed attention kernel. We observe near perfect scaling here as well until we reach 88 workers, or 1 worker per physical core. And this allows DAM to simulate a GPT-2-sized batched multi-headed attention layer in 14 seconds, costing less than a penny on a CloudSpot instance. Finally, DAM's CSP with time interface is also significantly more concise. On the left here, we have the original Python code for simulating a node, which repeats a signal based on another one. And on the right, we have the DAM-based re-implementation. DAM uses 57% fewer lines of code, despite using a more verbose language, and with significantly improved readability. And this is because the CSP with time interface allows the programmer to use software state to carry hardware state, which is normally achieved by introducing many auxiliary variables which need to be persisted across many invocations, as we see here in the yellowish orange. So, of course, there's a lot more that goes into this. More details can be found in our paper, such as time and synchronization, scheduling, how we have time-traveling channels, and additional case studies. The simulator core is publicly available on GitHub, following the QR code here. And if you have any questions about DAM itself, feel free to email me at stanford@stanford.edu. No, that's a typo. If you instead have questions about sparse tensor machine learning or streaming data flow, I've also included Ruben's and Gina's emails as well. Thank you.
Any questions for Nathan? All right, I have one while folks are coming up. So I realize, in the talk you couldn't get into as much detail on this, but can you talk more about your notion of essentially what assumptions you're making about work that can be done independently versus work that actually needs synchronization? It seemed like you were making some assumptions about, task A and task B, because they're independent, I can run them in parallel and get benefits, but I didn't quite understand how that changes if you need fine-grained synchronization, say.
So our execution model, we essentially assume that you've taken your architecture, your software simulation, whatever, and you've broken them down into a set of components, right, that communicate over channels. This is, right, your standard data flow architecture, and we also assume that all of the communication between them happens over these channels. So that actually results in a system where even though two tasks might be sort of at a high level dependent on each other, you can still run them at the same time as long as you sort of time skew one of them slightly slower than the other. Yeah.
Okay, next question.
The CSP plus time abstraction, there's some similarity with the A-ports work by Michael Pallauer and others, or even the ASIM work. Would you agree, disagree? Or?
So the CSP with time, at least as far as I understand, is significantly different from how your classical event-driven simulators work, and also similar to ASIM. We actually straight up don't have an event queue. And that essentially allows us to completely avoid global synchronization. To the best of my knowledge, all of those involves some degree of everyone has to stop and talk to each other to make sure we're all on the same page.
Okay, well, I'll talk to you at your poster.
Okay.
All right, if there's no other questions, then let's thank the speaker one more time. And that concludes session 5A. We will have the poster session outside right now for the next 30 minutes or so. And then keep in mind the business meeting will be in here in 27 minutes. So see you all back here very soon. Thank you again.